So here we are. I run a little bit behind in producing some of these videos, but I want to give you a heads up that we're going to have about 4 of them by the time that the quiz rolls around next week. So the quiz is going to be here on Friday of next week. So that'll be let's see, if today's the 16th, 15th, it'll be the 22nd. So the 22nd you'll have between noon and 10 o'clock to take the quiz. Probably 10 questions or so on the quiz. So things over the presentations I'm giving you. So we're completely separate from the lab part in here, but we try to track together on the same topics. But here we go. Science is the big talk we're talking about right now. And so science is a way to understand things. It's a way to not be fooled. It's like, you're going to, I guess what I'd like for you to learn in here is to become a skeptic. You can't prove anything, however, but at the same time you can disprove things. So you have models, and so we're going to try to show you how things are disproved, in other words, and how we build the model of how we think the world works, and that's the metaphysics of philosophy. So without further ado, I'm gonna go on to tell you a little bit about science. And thanks. Yep. So the nature of science and geology, and really we're going to talk about science first here. So some of the key points are you can't prove it. That's a statement that a lot of people say. And in science, that's absolutely correct. You can't prove it. What we try to do, however, is to build a case. And we do that by proposing a hypothesis and then begin testing that hypothesis. And we build arguments, essentially. In a way, it's a lot like a court of law. And so, you cannot convict somebody without evidence. In the same way in science, you can't present a case for a way that we view the world or a way that we perceive the world to act in a certain set of processes and a certain set of outcomes, if you will. And in geology, that experiment's already been run. So what we try to do is build arguments, and we try to build those arguments on evidence. And the evidence that we have can either be direct or indirect. And so, we place more confidence in arguments that are built on direct evidence, but indirect evidence sometimes is the only thing that we have. So we also build in science. We like to say there's good science and bad science. And the good science is we try to do multiple working hypotheses. Is there more than one explanation for the phenomena that we see or we experience? And so that's called multiple working hypotheses. And so you may have multiple explanations, in other words, to try to explain some sort of natural phenomenon. You'll hear people say it's only a theory, when actually in science, a theory is the best thing we can hope for. Theory means that it's a hypothesis that has been tested multiple times and over maybe decades. And if we can't disprove that hypothesis, we eventually incorporate it into our thinking or into the paradigm that we have about how we think things work. And so I'm going to introduce you also to a couple of people in this presentation. So a couple of the scientists or science philosophers that have been influential in helping us understand this sort of mindset for how the world can be evaluated or how ideas or conjectures can be evaluated. Karl Popper is one of these guys. Karl Popper was an Austrian philosopher of science. And it was Karl Popper who proposed this idea that you have to be able to potentially show anyway, that an idea is wrong. So you should be able to have some falsifiability to that hypothesis. And if you propose a hypothesis that can't possibly be knocked down by gathering new evidence, then you're really not doing science. And so that's what Karl Popper said. And it was Thomas Kuhn was the other guy. And actually he used geology as one of his case studies. Thomas Kuhn said that science advances in sort of leaps every once in a while. And those leaps, in fact, he calls them paradigm shifts about how we view the earth. And the biggest paradigm shift in geology, at least in the last 40 years or so has been this idea of plate tectonics. And so plate tectonics revolutionized the way that we see that the Earth works. And that is that it works with a series of broken bits at the outer surface. And so the crust and the outer part of the mantle work together in these lithospheric plates, and they move around through time. And it gave us a great explanation about how we see patterns, for the distribution of fossils, where we get mountains, where we have spreading centers in the middle of the oceans today, and also where we have subduction zones for instance, on the west coast of North America, and all the way up into Alaska and around the Pacific Rim. Essentially, it's the Ring of Fire. Actually, when we talk about volcanoes, we'll get to that at some point in here. So, okay, so why did I put Venus on this slide? This is, of course, not a science that gets limited to just the Earth. In fact, we can apply geology to all of the other planets that we can see anyway. So for instance, all of the terrestrial planets, it's easy to look at those, and we can actually do geology on Venus, for instance, and on Mercury, and we can also do it on Mars. And besides that, it's kind of our twin planet. If you want to think about it that way, Mars is much smaller than Earth, and Venus is almost the same size. And Venus, only recently, they've discovered phosphine, I think it is, in the atmosphere of Venus. And people have made a conjecture that's like, well, maybe there's life on Venus. Now, it won't be life at the surface because it's just too horrible conditions, I guess you could say, for life to exist on the surface of Venus. But up in the atmosphere, it can be relatively cool, or cooler anyway. And so maybe life could exist in the atmosphere of Venus. We're not quite sure yet. And I'm pretty sure that most people would say, no, that's not possible. But there are people who have proposed that idea anyway. And so it's a testable hypothesis. And so we'll maybe look at that when we get to planetary geology later. Okay, so if you can't prove it, that is a correct statement. You cannot prove anything. You do that in mathematics. So if it's in science, in the realm that we regard as science, if you can prove it, it's trivial. For instance, if I said that blue light is 300 nanometers a wavelength, that actually falls into the category of fact now. It's no longer a hypothesis, but you could say that blue light has a certain wavelength, and yes, and then people go out and they test it by measuring the wavelength of blue light. Red light has a wavelength also, but if you're to go out and try to prove this idea, that, let's say red light is 680, it's already known. Okay, so we consider that to be fact. So if you were to be able to prove it, which we could say, yes, you can measure it, and it is 680 nanometers wavelength, then, that's trivial. We already know that. So you can't really propose that as a hypothesis, in other words. Now, all of these sort of ideas, all these ideas about how we think the world works or how we think that the universe works, that all falls into a category known as metaphysics. And so metaphysics is a type of philosophy, if you will. How do things work? And how do we incorporate that into our own understanding of how things work? So that's a metaphysical proposition that we make with ourselves. And so we like to say in the natural world, it's like, I'm going to test hypotheses and see if this is actually a valid idea or not. And the ones that we consider to be valid, those are the ones that we incorporate into our understanding. And then those are also the ones that get put into the literature as well. So scientific literature. Now, oftentimes, you probably had a science course before, either in biology or chemistry or some other sort of type of science, maybe in high school, maybe here at the university as well. Oftentimes you'll see a sort of cookbook sort of way that they present this. And so now I'm here to tell you that cookbook is pretty much wrong. I mean, it's accurate in many ways. Yeah, we try to state a problem or ask a question, but oftentimes you're probably going to find that most science is actually in the fact that it's a discovery. And so discoveries are things that kind of astonishes us, like, wow, I found this thing and I don't know what it is, and so then you propose a hypothesis, then you can ask the question. And so oftentimes it's an outcome from some other sort of aspect of science. And so, but anyway, that's the cookbook here that gives you steps 1 through 6. You gather information on it, you form a hypothesis, you design and perform an experiment. And again, I'm going to tell you, in geology, most of those experiments have already been run. Okay, they're in the rocks. That's why we get rocks in certain parts across the continent. And it's like that's the experiment has already been run. So we try to figure out what steps went into making that experiment. So it's a lot more like forensics that we do in geology. And then lastly, of course, you draw a conclusion and you eliminate the ideas that were incorrect and you adopt the ones that you can't throw out. And so we adopt the ideas that are, well, it seems like this is still a viable explanation for why we see this. And those are the ones that we keep and those are the ones that we report on. So in fact, most scientists don't do that, It's like, but really what we're doing when we test a hypothesis, we're hoping to actually throw it out. Well, we don't hope one way or the other. It's either going to be that we accept it or we reject it. And so science is not a cookbook. So if the experiment's already been run, what we look at are things like mountains. We look at like glacial lakes, like you see in this slide, the upper right here. And then also we see things like banded rocks that we know could not have formed at the Earth's surface because, well, at the Earth's surface, there's not enough pressure to cause those rocks to be folded and bent like that. And then lastly, we can directly observe things in geology as well. So for instance, in volcanics, we can see those things when they erupt. We can see them when they explode, and we know what kind. We can go out and we can collect the rocks that are associated with them, and then we know what kind of processes may be going on then inside. So there's kind of an indirect evidence that we can get from the rocks that were ejected from a volcano. Okay, to give you an example here, all of you know that it's warmer in the summertime than it is in the wintertime, usually in the Northern Hemisphere. That's because the Earth's rays hit us more directly in the Northern Hemisphere because the Earth is tilted. The rotational axis of the Earth is tilted towards the sun during the summer months, and it's tilted away from the sun in the winter months, and so we don't get quite as much solar insolation. Now, proof of that would be if you were to look at sunrise and sunset every day of the year, you would find that the sun rises in the summertime in the northeast, and it sets in the northwest. It makes a large arc across the sky, in other words. And the only way to explain that is if we have a world or an Earth that is spherical. Because it's just the opposite of that on the other hemisphere. So if you're to go to Australia or New Zealand, for instance, and you can fly there, you can prove this to yourself. And you can see that the sun is more direct in the wintertime, that's their summer down there. In the North American winter, you're going to get a lot more sun in Australia and New Zealand. That's their summer, and they call it the austral summer. So that's one proof, in fact, that the Earth is not flat. So again, the Earth is not flat. So number two, and this is really kind of cool, and I only know this because I went to New Zealand, and one of the things that I did was in the starry summer night down there, which was during our winter here, I looked up in the night sky and I saw a constellation that was familiar to me. It was actually the hunter, Orion. And I looked up and I saw Orion, and I looked at it for a minute. I mean, it's easy to recognize Orion from the three stars that form the belt of the constellation Orion. You look up at that, and I notice it's like, oh, it's upside down. I was viewing it from the other hemisphere, looking towards the north, and that was, during in the wintertime, it's a winter constellation in the northern hemisphere. For them, it's a summer constellation, but it's on the northern margin of their skies. And so here it is. Here's Orion, and Orion, that cluster of stars, is upside down. And so it's not a star cluster, but these stars were upside down. That constellation was upside down. Again, the Earth is spherical. The Earth is nearly spherical anyway, and not flat. So that's a test of the scientific world. Now, people understood that like 600 BC, okay? That idea has been around a long time. In fact, it was Eratosthenes who tested that in Egypt during the equinox, I think it was, because the sun was directly overhead. He was right at the Tropic of Cancer, and looking up from a well, you could see a hand-dug well, and you could look directly up and see the sun passing overhead. Well, he measured the distance, and he actually made an estimate that was pretty close to what we understand the diameter of the Earth to be. It's within 10% anyway. So people have known that for a long time. So in other words, people are willing to lie to you in order to get you to believe them because they feel empowered if they can tell you that the earth is flat. So don't believe these fallacies. Don't believe lies, in other words. And that's what science is here to help us with. Science is a way to test to see if somebody is lying to us. And so here we are. That's one example right there. We ask a lot of questions in science as well because we want to understand how the earth works. And a lot of it happens by accident. You may observe something. So for instance, in this image that you see here, I discovered that actually. And so that is a round feature. It almost looks like an eyeball there. And you can kind of see where the pupil is and the iris around the pupil. And you can see a larger sort of dimension to it that is more or less oval shaped or round. And that actually turns out to be a meteorite impact site. And the evidence for it being a meteorite impact site is not because it has round features associated with it, but it's because it has shock quartz in it. And so it's quartz that's been exposed to high levels of pressure due to that impact. And so most impacts are really high velocity, hypervelocity impacts, and they generate a lot of energy. And that energy disperses through the target, which was the Earth at that time, at a relatively rapid rate. So hypervelocity sort of shock waves went through the earth there and it deformed some of the quartz grains that were in the rocks there. So what do you see when you see that? That is, it shows you the main impact area and it shows you a larger area that is the tectonic rim for this impact. So that's up around Osceola, actually. That's in between Springfield and Kansas City. So if you see that, you'll pass right through it on Highway 13 if you're heading north. So just a little bit north of the town of Collins, you'll see evidence for that in the rocks around, in between Collins and Osceola. But there are other explanations that could give you a round feature like that. Even volcanoes are round, in aspect when you look directly down on them. Igneous intrusive sometimes, once the overburden has been removed by erosion, will sometimes be round as well. There are other sorts of features that are round also. It can just happen naturally by streams cutting, in meander bends. It can cut around things, right? Well, there's a lot of meander bends in here and they're much smaller than that larger sort of feature there. So, but that's an impact site right there in our interpretation. And I'm pretty sure that probably won't be disproven at any time in the near future here anyway. So what do we do in geology? What do we do in the other sciences? We do sometimes inductive reasoning. Inductive reasoning says that we make a statement and we draw something from that statement. So if I said that every form of life we know depends on liquid water to exist, that's a fact, okay? Every form that we know of requires water. Therefore, all life requires liquid water or, it doesn't exist. And so, that actually could be false, so the supposition may be false in that case because we don't know that if we've seen all the different kinds of life forms because there may exist other life forms on other planets or even other exoplanets, planets that are outside of our solar system. We have 8 in our solar system, but they have found almost 3,000 altogether across the nearby stars, just the nearby stars around us. There are a whole bunch of these exoplanets that exist. So it gives you hope that maybe there are other types of life forms out there as well. Now, deductive reasoning is another type of reasoning, and we use that very commonly in geology. That's where you state a premise, you make an observation, and then you draw a conclusion from those two statements. So the first statement is the premise, everyone who eats a steak is a quarterback. Number 2, John eats a steak. Therefore, guess what? John has to be a quarterback. Now, in fact, that whole argument is flawed, right? Because it's not just quarterbacks who eat steaks, right? So the premise was wrong. And because the premise was wrong, and now John can eat steaks, or maybe he doesn't eat steaks. So maybe even the observation is wrong. But given the premise and given the observation, the outcome or the conclusion of this was actually correct. And so that's the way that type of reasoning works. So you have to make sure that your premises are good. And so premises are really important. So either has the potential of being wrong, of course. And so most geology is based on deductive reasoning. And here, of course, you can see a tiger who I assume is not eating John, but it is eating a steak. Okay, so that tiger is right there to show you that last statement was incorrect. So, as scientists, we belong to a school. In the Western tradition, we always give credit to the Greeks for first coming up with the Western civilization, if you want to call it that. And they developed some ideas, right? And so one of the things that we like to say is, I doubt it. And if you say that, you're actually being a skeptic. And so that's what, as scientists, we try to say. You may tell me something, and it's like, show me your evidence. It's a very Missouri sort of thing to say as well, because oftentimes we say that Missouri is the show me state, right? And if somebody says something, it's like, show me that, right? Show me your evidence, in other words, right? And so that's the idea behind the school of science that we belong to, and that's called skepticism. We're skeptics as scientists. We don't necessarily believe everything we're told. We read things, and we don't necessarily believe everything we read as well. So we don't like to get fooled, in other words. Karl Popper said that, science must be falsifiable. I've already mentioned Karl Popper on here, but that's his photograph over here on the left-hand side. He was a philosopher. If you can't disprove that hypothesis, then it's not a valid scientific hypothesis. And a hypothesis is a proposed explanation. And so that's what we try to test. Now, if we keep testing a hypothesis and we can never show that it's false, or disprove it is the other word that we use. If you can't disprove it, eventually we grow to accept it. And so that is, in fact, if it is a hypothesis that has a suitable test where you can actually show that it can be falsifiable. So in other words, a theory is actually pretty good then. If somebody says that's only a theory, that's like, yes, theories are really good. That's how we understand things. We understand a lot about gravity. We know that there's a behavior between gravity and the center of the earth, for instance. So objects are attracted to the center of the earth. That's why we can be on the outside of a spherical sort of object, because our gravity holds us down to that object, and that is the earth. And we're drawn towards the center of the earth. And when we can't disprove a hypothesis, we eventually begin to accept it, right? And so for gravity, it's very difficult to understand gravity because there are no particles associated with it. There's no energy. We can measure what the gravity is. We can measure the attraction to the center of the earth. And we can explain, even attraction, like if you're really close to a mountain, that mountain is actually trying to draw you away in that direction slightly, okay? But you have very small gravity compared to that of a mountain. We know that there are little nuances as you go across the surface of the earth where the gravity changes. And so, but just understanding that relationship is a little bit different than understanding where gravity comes from. And today we understand gravity more as being a sort of phenomena associated with the space-time continuum. And so the space-time continuum is this combination of kind of the first three dimensions and then time. Between those 3.5 or 4 dimensions right there, that probably is responsible for how gravity works. And so we can recognize how it works. In fact, people recognized that a long time ago. It was Einstein who proposed this hypothesis that, if you have a lot of gravity, like, for instance, the sun, it is going to be able to bend light. It's one of the few things that can bend light. And people tested that hypothesis during a solar eclipse. They could see the stars that they normally couldn't see because they were too close to the sun during that solar eclipse. And so they said, there's where those stars are right now that we see, but they knew that the gravity was still there, even though we couldn't see the light of the sun. And so 6 months later, when those stars are in the night sky, you can measure the distance between those stars again, and you can see that the light was bent. It was a guy named Eddington who came up with that hypothesis. Well, not that hypothesis. He actually tested Einstein's hypothesis, and sure enough, it showed that Einstein probably was correct in saying that gravity bent it. Does that mean that he proved that gravity bent it? No. It just showed that he could not disprove Einstein's idea. So that's Karl Popper who came up with that. Now, Thomas Kuhn is a different sort of level of philosophy. It was Thomas Kuhn who wrote a scientific paper. It's called The Structure of Scientific Revolutions. And so we go through revolutions in science all the time. For instance, people didn't used to know that there was a thing like DNA or RNA or any of these other sorts of things that we share in common with all living creatures on Earth, right? Everything has at least RNA or DNA. And that's how we can replicate, and that's how we metabolize things through time, I guess you can you can say, and how things can evolve through time because you change the genetics essentially, right? Well, it was Thomas Kuhn who came up with the idea that we go through a pre-paradigm. That's the old ideas, you could say. You call it pre-paradigm. There was a different way about how we viewed things, and we had different views of how the Earth worked before plate tectonics came along. And then people do the science, right? So somebody proposes a new hypothesis next and say, I think that the Earth works this way maybe. And it's like, and then people go out and test it. And that's when they do the regular science. And eventually, if people cannot disprove that hypothesis and they can disprove the old ideas, then people begin to accept the new ideas. And so that's the revolutionary part. And that's what they call a paradigm shift. And so paradigm shifts are these ways that we collectively change our understanding what science is. And so that's kept within scientific books. It's kept in textbooks to a certain level, right? That's the easiest things that we can understand are in the textbooks. So you're taking this geology course. You're taking this course. Is it going to make you a scientist? Well, maybe in a way. That's one of the things that we do in the labs. And in the labs, you can see that you can test certain hypotheses about, okay, if this is this mineral, then it should have this hardness, right? So that's the way that you might be able to do some science in this class. Otherwise, you're mostly going to learn some of the facts that we learn about in science, right? So you'll be doing science somewhat. In teaching the science, it's really good for us to show you how to do this, however, right? So I know, for instance, that I can drop hydrochloric acid on one mineral and it's going to behave a certain way, and other minerals will not behave that way because they may be impervious to that dilute hydrochloric acid. So anyway, we build these sort of ideas. And so you can see in this image, testing the hardness of what seems to be something that is scratchable by a knife blade here. So I guess that gives you a little bit of an introduction what we're going to talk about next, and that is, what do we look at in geology? What kind of things do we study? So I'll leave it there for now, and I'll check back with you very shortly here. I'll get these things uploaded either today or tomorrow. So anyway, hopefully this will give you an introduction to what science is, and will give you the introduction to what geologists look at next. Thanks a lot. Talk to you later. Bye now.